Hello, everyone. Can everyone hear me? Hopefully you guys can. Sorry. I'm gonna stop. Oh no. Give me a second. I'm just gonna open up the QR code page. Give me a second, please. All right, here you go. Please sign up your tenants. And also the link is in the chat as well. Please let me know if you're done, and then we're just gonna get started for this tutorial. And also you'll need to download the tutorial sheet from Canvas. So this is week 9, schema refinement and normalization. All right, can I assume everyone is done? Okay, so I just stop share. Okay, so we can get started for the tutorial. So just let me know if you just came in and you didn't have a chance to sign in. Just post a link in the chat again. All right. Okay, tutorial week 9, schema refinement and normalization, which is a pretty interesting topic. So exercise 1, interpreting functional dependencies. Consider the following schema regarding the, I guess we've got a couple of questions then, a couple of more questions than we'd expected. So I don't think everyone will have time for breakout rooms. So we're gonna do all these questions all together, all right? So consider the following schema regarding the transport of important passengers directly from a specified pickup point at the airport entrance to the appropriate departure gate for their flights. So the table name, VIP transfers, where we have 7 attributes: destination, departs, airline, gate name, contact pickup. So the entries or tuples in the table will be like Berlin, a time. So the time corresponds to departs. So just bear in mind, departs referring to a time. And airline, Lufthansa, gate 3, name just in time. And contact here and pickup 1 means that just in time has a flight to Berlin at this time with Lufthansa Airlines departing from gate 3 and must be taken there from pickup point 1. And Justin can be contacted by phone on his number in here. And the schema has the following functional dependencies. So many of the students will have some misunderstandings about the functional dependencies. So when we talk about FDs, we're not about to assess if it's wrong or right. So these are just the functional dependencies. It doesn't actually mean gate is dependent on the combination of the destination, departs, and airline. But in terms of design of the tables, just by looking at destination, departs, and airline, we should be able to determine which gate that is. So that's why we call it like functional dependencies. Doesn't necessarily mean the gate can be determined from there, but just by looking at the table, we should be able to determine. That means the combination of these three can only lead you to exactly one gate. So if there are like two gates that can be directed by looking at these three, that'll be a violation against this FD. All right, so we have 5 FDs in this table. And for future use, I'm just copy and paste these and assign a name to them. So next time when we refer to them, I'll just refer to them as FD1, FD2, and up to FD5. So FD, FD2, FD3, 4, 5. All right. So question 1. Express the above functional dependencies in simple English. So I guess the best way to go about doing this question is like, you might want to use the keyword like functionally determines, which is not the perfect way of doing that, but definitely you can. So we could always argue that left-hand side functionally determines right-hand side. If we don't actually want to get a sense of that, like you would argue that the combination of destination, departs, and airline functionally determines gate. But if you want to get a sense of that, you would notice that destination, departs, airline, and gate are related to flight. So a flight has a destination departing at a time with an airline, and that particular flight will only be assigned to exactly one gate. So you might want to say there shouldn't be more than one gate that should be assigned to a flight if we know its destination departing at a certain time with a certain airline. So the correct way of express this functional dependency could be an airline never runs more than one flight departing at the same time to the same destination with the same destination. Yeah, and each of those flights should depart from a single gate. And similarly, you would also argue that there should be exactly one airline departing at a certain gate. So this is a second functional dependency. Third one, from contact to name. That means if you know the contact, we know who the person is that owns the contact. So that means, so don't get the other way around. Like you can't always go from right to left, but from left to right. So what if a person has like 2 contacts? Is that also feasible in this table? I think it is, just because by looking at the contact, we know that we know who the person that is. But what if there are 2 people who share the same contact? Is it allowed in this in this context? No, right? So from that particular contact, you will trace back to 2 people. That means by looking at the contact, you don't know who the person that is, which you were just going to see in question B. And next, name, departs, gate, and pickup. So that means a VIP cannot depart from 2 gates at the same time and cannot be picked up from more than one location for departure. Lastly, gate departs to destination. So a flight has a gate departing at a certain time, and there should only be one destination for that particular flight. So flights can depart to at most one destination, departing at a certain gate given a certain time. All right. So we would always find like a way to express the meaning of those functional dependencies, given that is true. All right. But just bear in mind that if you're just running out of time, you wouldn't have enough time to think about like what the FDs mean, and you would also write like gate functionally determines airline, that will also get you a partial mark if you're just running out of time. You don't have time to think what it actually means. All right. Next question. Question B. Consider the following collection of tuples. Why is this instance not a legal state for the database? So firstly, what the question is asking is like, what is a legal state? That means all the tuples can be verified against all FDs. So you're going to look at all those tuples and compare them against all those FDs. So if there is any violation, this is not a legal state. Yeah. So following that, can you identify any errors or violations against those FDs so that I can verify this is not a legal state? Sorry. Can anyone identify any violations? Yeah, Joseph, gate 7 against 2 airlines. Against 2 airlines, what do you mean against 2 airlines? So gate 7, we have 7 here and also here. But by comparing that with FD2, so from gate to airline, that means each of the gate should direct you to exactly one airline, right? Do we have the same airline for gate 7? No, we have British Airways and Cathay for the gate of 7. That means, I guess the proper way of doing that will be you would always you're just about to nominate which tuples you're looking at. So tuples 3 and 4, 5, 7, 6 against FD 2. Yeah. So I guess that'll be a correct way of identifying one violation. Are there any other violations? So what about contact to name? Can this FD hold across all these tuples? I think no. So if we're looking at 563, so we have in the first tuple 563, which is owned by just in time, and this 563 is for ricochet. So this is a violation against FD3, right? So this is second violation. Tuples 1 and just 1 and 4 against FD3. Right? Okay, next one, tuples 6 and 7, as I can see in the chat. So 1, 2, 3, 5, 4, 5, 6 and 7. Yep. Which violation it is against? Which one? FD4. So we have name and departs. That should determine the gate. So 5, 6, 6 and 7. So we have departs exactly the same. And also name you go first is the same as well. And well, What gate do we have? So we have 7 and 2 for gate. That means this is a violation again against FD4. Yeah, that's right. So this is how we argue that this instance is not a legal state for this database. All right, but in the exam, only one violation would suffice. Okay, unless you are asked to identify all the violations. All right. Okay, next question. Exercise 2. Candidate keys and normal forms. So candidate keys. So before we go further into the question, the first question you want to be very familiar with is that how would we be able to identify or determine a combination of attributes as a candidate key? Did you get my question? So before we go to the concrete questions, the question I want to firstly ask you guys, sorry, why can't I get a 2? Okay, what is it? Why is? Okay, anyway, you know what I'm talking, what I'm writing here. Okay, so how could we determine a combination of attributes is a candidate key? How do we do that? You may just want to unmute yourself if you want to speak, all right? Otherwise, you can also type in the chat. Minimal super key, yeah, that's right. So first condition, that'll be, we're gonna verify this is super key. How do we verify this is super key? By doing what? Calculating the closure, right? So what we are trying to find in here is that by calculating the closure of the combination, we're trying to find all the attributes, right? If we can't, that means it's not a super key, at least. Second step, we're going to calculate or any subset of the combination. What we are trying to find in here is that they shouldn't find all the attributes, right? So by doing the first step, here we are trying to verify this is a key, but the second step helps you identify this is a minimum. Make sense? So that combining these all together, this is going to be a candidate key. All right. So we've got 2 steps in here. All right. Question A. Is contact departs airline a candidate key from the above functional dependencies? So having said that, the first step is to calculate the closure of this combination, right? I hate the format, it's so messy. Anyway, as long as you guys understand what I'm doing here. So how do we calculate closure of this combination? The way we go about doing that is by looking at all these FDs, right? So first FD, can we apply here? No. Why? Because we don't have destination. And what about gate? No, we don't have gate. And then contact? Yeah, we have contact. So by applying FD3, we're going to get the first step of calculating the closure by adding which attribute? name, right? And get rid of the plots in there. And next, which of the can we apply in here? We have contact, name, and departs. So now we're able to apply FD4 just because we've already got name and departs in our combination. So what is it? Gate and pickup. Yeah. How many attributes do we have now? 1, 2, 3, 4, 5, 6. So next one, last one. Which one is missing? Destination. Yeah. So the last one we can apply here is FD5. That helps you to get all those attributes. All right. So this is first step. And second step, we're going to verify any of the subset of this combination cannot get all those attributes. However, if you do want to calculate this combination, what is the combination? What is the closure of this combination? Can we also get all those attributes? Yes, right? Why? Because if you compare these two, so the airline is the one we are missing here. However, so contact can get you the name, and name and departs together will get you gate, and gate determines airline. That means airline can be determined from this combination, all right? So that means the closure of these two also equals all attributes, right? So this verifies that this is a super key, not a candidate key. Okay. Did I make myself clear to everyone? Yeah, so we're following 2 steps. Firstly, calculate the closure so that you can see all those attributes. And next, you're going to verify any of the subset of this set so that they can't actually get you all those attributes. And then you can come to the conclusion that this is a candidate key. However, in this instance, we can determine that this is not a candidate key. Next question, how can you find an alternative? Can you find an alternative? So the first way I go about doing this question is that we've already got this can also be a super key, right? Because we can get all those attributes. So next, what you can do is calculate the closure of contact alone and also the contact of departs alone as well, so that you can see the so neither of them will get you all those attributes. So this further determines this combination is a candidate key, right? Is that clear, everyone? But the next question I want to raise to you guys is that what if we don't have this assumption in the first place? What if the question is asking, like, can you find a candidate key as the first question? How did you make the first assumption in the first place? So how do we propose a combination that could be a candidate key in the first place? So saying that in the first place, I mean, if we don't get this question, if we don't get this proposal as the first in the play, as the first instance we want to verify, So how do we, what is the first combination you want to propose? Anyone? You got any thoughts just by looking at these FD? So, all right, just I just rearrange my words, like I just rephrase that. So what if we don't have this question? And the very first question I want to ask you guys is that what is the first combination of candidate key you want to verify? Can you just go look at these 7 attributes and just randomly pick up 3 or 4 or 2? Is that feasible? No, obviously, because you're going to verify very hard, right? So I guess the best way to solve this question is that you're going to find attributes that only appear on the left-hand side, not on right-hand side. Why? So think about it. If you're looking at these FDs, if there is an attribute that only appears on the left-hand side, but not on the right-hand side, what does it infer? That means that particular attribute cannot be inferred from other attributes, right? Make sense? So what is the attributes that only appear on the left-hand side in this instance? Contact, yeah, that's right. Contact only appears on the left-hand side, but on the right-hand side in all those FDs, we can't find contact. That means contact must be part of the key. All right. And also what? Departs. Yeah, that's right. Did someone say name? Can you find name on the right-hand side? Yes, you can, obviously here. All right. That means name is not part of the key, but contact and departs are part of the key. All right. So the very first combination of attributes you want to verify is contact and departs. Yeah. All right. This is how we do this kind of question in the first place. Like, what is the first combination you want to verify? Okay. Second question: is this relation in second normal form or third normal form? Sorry. How many conditions we will need to verify against so that we can verify this is in third normal form? How many criteria or how many conditions is in there? So if you're not too sure, just go to the slides where you can find, yeah, that's right. First normal form, second normal form, and one more condition. So that'll be 3, right? So first condition, what? No multi-valued attributes, right? Second, what is the condition for second normal form? No, what? Partial dependency, right? What is a partial dependency? So if you go to the lecture, so partial. So we know the key is A, B, and C, while in the same time, A and B together would also determine D. That means AB as part of the key can also determine some other non-prime attributes. That means this is a violation against second normal form. So this table is not in second normal form. And on top of that, the third condition is no transient dependency. All right. Dependency. Yep. What is a transient one? So you may need to go have a look at this slide. So we have K as A, B, C again. So A, B, and C determines D, but D also determines D, E, and E determines F. So this is like a passing, so that this is a transient one. And what it says in here is that if you violate any of those, the relation is not going to be in third normal form. All right. So just by looking at these, are there any violations against the three conditions here? Obviously, yes. First normal form. What do you mean first normal form? Do we allow multivaluing here? No, we don't. Right. So all of those attributes will only allow one value. That's why you can see Berlin and time and Lufthansa. So we don't allow multivaluing here. What if we have Berlin and Madrid at the same time? That'll be a multivalent one. But we don't have it here. That means this this condition has been satisfied. And what we can find in here is that just because we've already verified contact and departs as a candidate key, and gate to airline is actually a violation. Why? Because gate is not in part of the key. Gate is not part of the key. That means gate can be determined somewhere else from these two, and also gate determines airline. That'll be a transient dependency, right? Do you get what I'm talking? What I'm saying? So the conclusion to this question. No, I mean this is the question B. Right? Why do we have C here? I don't see why. Anyway, we are doing second question, so not in third normal form. Just because we've already identified a transient dependency. All right. So next question. Explain whether it is a lossless join decomposition to decompose the relation to the following. 1, 2, 3, 4. Okay. So how do we determine if it is a lossless join? How do we do that? What is the definition of a lossless join? That means join the smaller tables, you will get exactly the same as original one. So that means when you join R1, R2, R3, R4, this is going to give you exactly the same as this table, right? However, you are not able to verify just by looking at these, and we can't actually join them. So how do we do this kind of question? Like, do we have any other verifying way so that we can verify that? Actually, that is also in the lecture slides. Where is it? Give me a second. Yep. So lossless join. A conclusion that can be derived from the definition in here is that a decomposition of R into S and T is a lossless join if and only if the common attributes of S and T are either superkey of S or superkey of T. Makes sense? Right. So following this conclusion, can we determine if this is also joining or not? Any thoughts? No. We can easily verify R3 and R4 just because if you're looking at these two, I mean, in here, so gate and airline, contact and name. If we are trying to remove airline from the original set, we're going to get a smaller table that consists of gate and airline, which is R3. And next, we're going to remove name out of the original attributes. That'll be a combination of contact and name, which give you R4 as contact and name. What if we remove our airline and name out of all those attributes? What are the ones that are left? So I'll just copy the original 7. And I'm going to delete the one we can get from FD's, R3 and R4. That'll be airline and name. So airline can be inferred and name can also be inferred. Names, right? Yeah, airline and name. We delete it from the original table. And the left ones are these 5: contact, departs, gate, pickup, destination. So if R1 and R2 join back, if they can get this combination, that'll be a lossless join, right? So can we do that? You may want to refer to the definition in there. What if this, let's say this is if R7, let's give it a name so that we can refer to it more easily. So a decomposition of R7 into R1 and R2 is a lossless join if and only if the common attributes of R1 and R2 are either superkey of R1 or superkey of R2, right? So what is the common attributes of R1 and R2? It'll be departs. Okay. So next question we are gonna ask is departs a superkey of R1 or a superkey of R2, right? That means just by looking at departs, you should get destination and gate, and also depart, and also contact and pickup. Yeah. However, if you're checking that against all those FDs, you can't just by looking at departs. So we have departs here, but if you just use departs, you can't actually get all those attributes, which means departs is not a superkey of R1. Departs is not a superkey of R2. And that further means the common attributes is not a superkey of S or T, so that the decomposition of R7 is not R1 and R2. So this means it is not a lossless join. The other way of describing this kind of join is like a lossy join. That'll be a lossy join. That means if you join back R1 and R2, you will get actually a couple of more tuples than we have in here. All right. Next question, give a lossless join decomposition of the regional relation into BC and F relations. Okay. So just because we've already finished question C, we know that R3 and R4 can be a legal decomposition as per the definition of BC and F. So let's just use R3 and R4 before we can further decompose R7. All right. So we have R3 and R4. Again, why? Because based off FD2, we can get R3. And based off FD3, you would get R4, right? And next question we're gonna ask is, if you wanna decompose R7, what is the FD you're gonna use to decompose it? The candidate FDs are this one or these two. So which is the one you're gonna use? Can we decompose R7 using the first FD? Which one can be employed? I guess it's the easiest one to verify. Why? Because we don't have airline there. Yeah. Destination departs airline. However, you would argue that by using R3, airline can be determined by gate. So what if we change this airline to gate? This is going to be a valid FD as well, but that'll be a trivial one. Why? Because we have gate on the left-hand side and also gate on the right-hand side. From this combination, you obviously will get gate because gate is also appearing on the left-hand side. So that'll be a trivial one. We're not considering any trivial FDs, okay? So what about the next two? Which one can we use for the decomposition of R7? The last one. Yeah, the last one. Why? Why can't we use this one? So we have name departs. Obviously, name is not appearing here. However, name can be inferred from contact. What if we change the name? What if we replace the name here with contact? Is it going to be valid as well? Can we use this? But obviously you are right. So this is the one we're going to choose. But why is this not applicable? Any reasoning? Guys, why can't we use this one? So do you guys remember previously we've already identified the combination of contact and departs can be a candidate key. Yeah, previously we did. What does it mean? What does the candidate key mean? It means the closure of this combination will actually get you all those attributes, right? So if you're using this FD, you're going to remove gate and pickup. So I mean, if we are going to use this, so next I'm going to delete these, but for now I'm going to do an experiment with this FD, okay? So what if we are using this one? You will firstly get a smaller table of these 4 attributes, right? So this is the first smaller table if you are using this FD. What is the one that what are the attributes that are left? So you want to delete gate and pickup from this combination. So you will have 3 left. That will be these 3. And if you're looking at these 2 smaller tables, their common parts are contact and departs, and both of them are super keys. It means by looking at this combination, you can get gate solely alone, and also can get pickup and destination. It doesn't actually make any difference to this relationship, right? Just because R7's primary key, candidate key is contact and departs. And for this relation, the key is also that. And this relation also has a primary key as contact and departs. So it doesn't make any sense if we're using this combination. However, if you use gate and departs, that'll be a different thing. So next one, let's say it's R1, 2, 3, 4, 5. Okay, so R5 is going to be derived from this attribute. So it's going to have 3 attributes in there. And also we're going to delete destination from R7 so that we can have R6 destination, right? So we're going to delete the right-hand side of those FD. So this is the last table we can have. So the resulting smaller tables will be R3, R4, R5 here, and R6. And this is derived from FD5. So we only used FD2 and FD3 and FD5. So that means that will just give you an intuition that not all those FDs are going to be used if you are doing the decomposition. We're only going to use the, useful ones. All right. That means if you join R3, R4, R5, and R6, it is going to give you back the original table, where you have this kind of instance. All right. Hopefully no questions up to now. If you find it a little bit difficult to understand, you would also need to refer to these definitions and think about why we have this conclusion. All right. Just because we are doing the decomposition based off the definition in where is it? Yeah. So in here, suppose we have a schema R and non-trivial dependency X to Y causes the violation of BCNF. We decompose R into R1 and R2. The first smaller table is going to be X union Y, like this. And next we're going to remove Y from the whole set of attributes. We're going to form R2. So just by looking at these, R1 and R2, so the common parts of them is going to be X, right? And X is either superkey of S or a superkey of T. So S and T will be respectively be R1 and R2 in this instance. This is why we have the conclusion like this from the decomposing methods like this. All right. Okay, next, exercise 3, relation decomposition. Download the VIP transfer.sql file from Canvas, which contains a schema for the above relation, along with the example data. Execute the statements within this file. You can insert projections of the original relation into decomposed relations. For instance, relation examples, contact name can be created as follows. And we're going to insert examples in there. All right, I guess we are going to use pgetmin4 for this implementation. I just stop share and I'm going to use pgetmin4 later on. All right. I'm just going to import the solution to this question so that I can see the effects of the decomposition. I'm not going to bother writing all those EDL statements. So just because I think you guys know how to write the correct syntax already. Okay. All right. So we've already created a table that corresponds to the original one where we have 7 attributes and we inserted valid values. How many we inserted in here? 1, 2, 3, 4, 5, 6, 7, 8. All right. We have 8 tuples in the original table. And next we're going to decompose those into R3 and R4, R5, and R6. So all those correspond to our design previously. Like we have these 3, destination, departure, and gate in R5 based off FD5. And then we remove destination from R7. So we have these 4 left. So these are exactly the same as what we did in exercise 2. And we're going to insert into these smaller tables with the same values from the original table. The way we go about doing that is to use the syntax like insert into R3, select distinct gate and airline, because we have gate and airline for R3 from VIP transfer. This is the original table. All right. So this way we can minimize the risk of neglecting any of those tuples from the original table. And then you're gonna execute it, commit successfully, so that we now have VIP transfers and also R3, 4, 5, 6 already in our database. So next I'm gonna what if you select from VIP transfers? You will obviously see the 8 tuples we've already inserted. So we have 8 here. All right. What if we are going to select everything from the R3 and R4 and R5 and 6? So R3, natural join R4, natural join R5. So we're joining all those tables all together. 6. And what can we get from the tables being joined all together? Oh, sorry. I'm going to just look at which tables can be naturally joined. So we have contact name in R4 and contact is also in R6. So what if we have R4 and R6 being joined together in the first place, and then natural joining with R3, I guess that'll be feasible, and also R5. What? Use the error in there. Oh, sorry. I guess that'll be the issue. So it's not about whether we are joining them in the correct order. They should also be fine if we change the order, right? Anyway, we're putting all those R tables together so we can see the results in there. So we can actually get 8 tuples, right? So this helps verify that this is a lossless join. So we have 8 tuples back. All right. Just for you guys to know, a lossless join doesn't actually mean there shouldn't be something missing. If there is something extra, if you join them back, this is going to be a lossy join as well. Just don't be fooled by its name. But what you need to know is that if you can get exactly the same table as the previous one, you are doing a lossless join perfectly. Okay. All right, I guess that's it for today. Thank you guys very much for coming to this tutorial. So if no other questions, I'll just leave it for today. And if any questions, you can just ask me or you can raise a question on ad forum. All right. Thank you guys very much. I will see you next week. The Word document? Yeah, sure. Looks like a little bit messy, I guess, but only if you can understand what I was writing there, that'll be fine. All right, let us save the file. Wait a second. All right, I can find the file in the chat. So I'll just close up the session if you've downloaded it. Okay. I think we are done for this tutorial. Thank you.